Welcome to this Node Bible entry about the distance from geometry node. With this node, we can calculate the distance from one piece of geometry to another piece of geometry, and then using that distance, generate a mask to drive proximity-based effects. Let's dive into Houdini to see how it works. In our scene, I've just set up a simple example to show how this node works. So first, we just have a grid. I've just increased the rows and columns to 100, so we have a few more points to work with. And then we just have a simple sphere that I've dropped down, which will act as our reference object. Now, if we go to the distance from geometry node, we see that we have our sphere templated, so we can see what it's actually calculating the distance from. The geometry we want this attribute to go on goes into the first input, and then the geometry we want to calculate the distance from goes into the second input. Now, at first glance, it doesn't really look like this is doing anything, but if we go up to our geometry spreadsheet, we can now see there's a new attribute called dist. Now that dist is calculating how many meters each one of these points is away from the surface of our sphere. We can see this point is 6.57 away. And as we go down the list, we can see that the distances get smaller and smaller. Now the geometry spreadsheet is great for investigating the different attributes, but to actually see what it's doing in the viewport, we can go up to this visualization toggle right here. And if we click, we can see a nice representation of those values in our viewport. You can see purple is mapped to the lower values, and it goes all the way up to red to the highest values. Now, depending on your scene, you might want to change this visualization around. And so if you go up to our visualization toggle and hold Control and click, you can actually change the maximum value. And so if we want the maximum value to be mapped to 5, let's just change the value from 10 to 5. And now red will start being shown at about 5 meters. It's worth noting that this visualization doesn't actually change anything with the attributes. It just makes it easier to see what values we have on our geometry. If we move our reference geometry around, we can see this node updates dynamically. So whether you're using the results of a simulation, adding keyframe animation, or even just manually moving it around the viewport like this, all the points on this grid are constantly updating. Let's take a quick look at the parameters on the distance from geometry node. First, we have the group, where, like many other Houdini nodes, we can specify a specific region or group that this node impacts. So here I've set up a group on half of the points on this grid. And if we just go and toggle on group underscore half, which is what I've named it, you can see that we only calculate the distance on this half of the geometry. Now, the reason that you'd want to use this occasionally is if you have a really large piece of geometry, a really dense piece of geometry, it can make it a lot more efficient to only calculate in the regions that you need to calculate rather than doing it over a whole big area. I'm just going to clear that out. Like many other nodes, we have the option to specify whether it's a point, vertice, edge, primitive group. In this case, it was a point, but I think generally, if you just leave it on guess from group, it's going to work out well. The next thing that we have is the reference group, and the reference group refers to the second stream of data coming in. And if you don't want to calculate from all the geometry that you have plugged in here, you can simply specify in the reference group which one you want to set up. So I've just set up the second sphere as a background sphere group. And if we just select that, we can see it only calculates the distance from that specific sphere. Up next, we have the reference group type. And this refers again to the secondary input coming into our distance from geometry node. By default, it's set to primitives, which actually take into account how far away our geometry is from the surface. But we do have the option to change it to points. And when we change it to points, it just takes each point on the geometry that's going into that second input and calculates the distance from each of them. Similarly, if we scatter points along our geometry, which here I've scattered 10 points, and plug that in, it'll calculate the distance from each of those points. When we change it to points, it does disable this distance metric parameter. So we'll switch it back to primitives and plug in our spheres. Talk about that. There are a few methods for calculating distance under the distance metric parameter. By default, it's set just to calculate the distance from the outside of the geometry. And so this will give you positive numbers based off of how far each of these points is from the outside of the geometry. Also, we'll get negative numbers on the inside of the geometry. The next option is you can actually invert that. So instead of distance outside geometry, we can do distance inside geometry. And that will flip our attribute around, giving us positive values on the inside and negative numbers on the outside. Our last option is distance from surface. And so this will give you the absolute value from the surface rather than calculating from the inside or outside. So inside the geometry will have positive numbers and outside the geometry will have positive numbers. Up next, we have our output attribute and we have a toggle. And so if we don't actually want to output anything, we can toggle this off. So this is essentially making this node pass through and it's not calculating anything. And so if we toggle it back on, we get our attribute back. And then we also have the option to name this any string. Now, typically I would recommend just leaving this as dist. But for example, if you had multiple distance from geometry nodes, you could do dist A as one attribute, and then dist B as another attribute, dist C as another one, if you need to control them all separately. But for now, let's just leave it as the default of dist. Now, having this distance attribute can be very useful, but what makes this node really powerful is the ability to remap that attribute into a 0 to 1 mask. So if we go ahead and just toggle on our output mask parameter, we can see that we get a new attribute here that ranges from 0 on the low end to 1 on the upper end. And that's going to make it a lot easier to blend effects and manipulate other attributes with that value. So if we go back to our scene view, let's go ahead and change our distance metric back to distance outside geometry. And then we can go over to our output mask parameter and visualize that instead. So here you see that we have a red to white ramp where red equals the mask value of 1, which is inside and right around the outside of the sphere. And then it ramps down to 0 as we get further away. We can adjust that radius by changing this radius parameter right here. So we can pull it in tighter, or we can expand it out further. We also have the option to calculate the radius from a maximum distance. And what that will do is it will find the maximum distance on our geometry and create a smooth ramp based off of the maximum. I prefer to keep it on the parameter and explicitly define it. So let's just change it back to 3. Up next, we have this remap ramp. So if we want, we can adjust our mask based off of this ramp. And so if we take this value, we can crunch it in and expand our mask out further from the surface of the sphere. And we can pinch out the fall off to make it a little bit sharper. Or we can even invert our ramp so that we have values of 0 on the inside and values of 1 smoothly ramping as we get further away. I'm just going to reset this to the default here. Now that we know how to generate a mask with the distance from geometry node, let's go ahead and put it to use. So I'll drop down a mountain node and just plug the output of our distance from geometry node into it. Next, I'm just going to adjust our amplitude to change it up a little bit. I'm going to make our amplitude 0.5, and I'll increase our element size to 1.4. Then I'll scroll back up to the top and toggle this blend parameter and change it from constant to use attribute. And what you can see is that it's already by default using the mask attribute that we generated in our distance from geometry node. And so as we get further away from our spheres, the influence that the mountain node has is blended away. We can go back to our distance from geometry node and dynamically update what this mask is doing. And so if we want the influence of the mask to extend out, we can slide our radius up and that will update dynamically. If we bring it back to 3, we could invert our ramp, like I had mentioned, by pulling this anchor over to this side and this one over here. And so now you have a nice fall off where you have full influence of the mountain node further away from our spheres. And as we get closer to them, it diminishes down to 0. And this is where a whole world of possibilities can open up, because you can add multiple spheres across the grid. You can reshape the fall off and really precisely control how we want to blend things on and off. To wrap up our discussion on the distance from geometry node, I've set up a few examples of this node in action. Similar to our mount node example, we can use our distance from geometry mass to drive deformations. For this example, I've imagined some sort of creature moving underneath the ground and deforming it as it moves along. To control this effect, I just animated a sphere close to the surface of the ground, and then using the distance from geometry node calculated how far it is. From that distance, I generated a mask, and then using a blend shapes node, we can use that mask to blend between deformed geometry and base geometry. So for the deformed geometry, I've basically just taken the same grid and translated it 1.5 meters up, and the result of that is this deformation of the ground rising up when it's close to the sphere. We could run any other type of deformation on this. For example, if I increase this to 3, we would get more of a deformation on our surface, or we could even add a different mountain node that increases the noise as our geometry runs over it. And so if we took the amplitude up to 3, we get a really abstract effect of mountains growing and rising as our reference geometry moves along. This can be a really great way to maintain base control over deformations that you can then run simulations over. In this next example, I'm using the distance from geometry node to control the radius and speed of a shockwave effect. If we go into Houdini, you can see all I've done is changed our distance metric to distance from surface. That way we get a nice mask that is only within a certain radius of the surface of our reference geo. I then use that mask to add some noise into our geometry as it expands out. You can see that in real time if we pull up this flipbook. And so here along the bottom, you can see our mask as it expands with our reference geometry and how it's deforming our grid. Up top, you can just see our raw distance visualization. If we hop back into Houdini, though, I'm also using it to just scatter points. And I've put the density attribute as our mask that's coming from our distance from geometry node. So that means as the reference geometry moves out, it's scattering points denser closer to the surface of our reference geometry. This makes it really easy to control the effect, and we can change the ramp in our distance from geometry node, or if we have to reanimate the timing of our shockwave, we can just simply reanimate our sphere up here. And then last but not least, I'm plugging all those points into a particle simulation inside a PopNet, and we get our final result here. As we look at our final example, we can start to think about some of the relationships we can dynamically build using the distance from geometry node. In this dust wash example, we're driving the effects starting with our distance from geometry node and the mask attribute it creates. Similar to our other setups, this one starts by calculating how far the animation is from our ground plane. So as our geometry comes down closer and animates, our mask will get stronger, and then as it flies away, our mask gets weaker. From that distance, we can generate that mask and define how many points are scattered on our surface. I've run a particle sim just based off of how close we get. I also, with a little bit of X, remapped that mask attribute to be a multiplier of our velocity, and so our source velocity will be stronger the closer our animation is to our surface. Once we've generated these points, we can rasterize their attributes and run them through a volume sim. All the data being fed into our dust simulation is being initialized with our distance from geometry node, meaning that when the animation gets closer to our ground plane, we'll get more points generating density and more velocity on each of those points. When our animation goes away from our ground plane, we'll get less density and less velocity. The benefit of creating a procedural setup that is driven by proximity is that we can update our animation and get a whole new result without having to change too many of the settings. In this example, I've just redone the animation and rerun our simulations. And because the effect is driven by our distance from geometry node, it'll update automatically. And other than changing our animation, all we have to do is resimulate and we'll get a whole new result. Thanks for watching this Node Bible entry on the distance from geometry node. If you want to check out more Node Bible entries like this one, be sure to head over to cgforge.com, and we'll see you next time.